Okay, do you have any questions? Okay, we have been discussing this. Now we have been discussing this motion in one direction, we have been discussing the acceleration, and finally we have discussed how does an object vertically thrown upward behaves close to Earth. Now of course if you just take this object and give it such a huge velocity that it reaches the boundaries of space, the acceleration will be different. But as long as the object is close to the surface of the Earth, if it just moves, let's say, a couple of kilometers at most, the acceleration will always be the same. So it's just an motion, it will just carry out motion with constant acceleration. Now for the time being, we are only discussing how we can describe the motion. We are not yet asking the question what causes the motion and what changes the motion. We are not discussing about force yet. Now we will start discussing force probably in 2 weeks, not even maybe next week we might start. But any questions up to this point? Now let's do one more thing. Dimensional analysis. Now again we are discussing this one-dimensional motion with constant acceleration. So one of the parameters that we have related with our problem is the acceleration. And its unit is meters per second squared. Now for notation I will be using, let's say this is the notation I will use, and this I will mainly mean by the dimension of A, whatever A is. Now in this case, if it's acceleration, its dimension is meters per second squared. Now we can ask the question, what is the, let's say you just release an object from a given height, then the question is how long does it take to fall down? So this is another property of our question, let's say the height, that is meters. Then the question asks you, how long does it take to fall down? Of course, we already have the equations. You can solve the equations and find the time. But you can do something else. In this simple example, we can make a demonstration of this. Now, we are also throwing an object. It will have a mass whose unit is kilograms. So this time, okay, we have solved the equations, but let's forget the equations for the time being. You have this problem. The problem has these 3 parameters. The acceleration might, ideally it can change. Although on Earth it will be the same, but the time might depend on the acceleration. It will definitely depend on the height. And in principle, it can also depend on the mass. You just drop it, and the time it takes to fall down, it can depend on the mass. Okay, we have solved the equations, and the equations tell us that it doesn't depend on the mass, but let's just forget that for the time being. Because to obtain that relation, we had calculated all these areas, we have evaluated integrals, and the calculation can get even more complicated. But here we will just go do an alternative analysis, which will not do any of these. Now we know that the time should depend on all of these quantities. It can be, let's say, some constant. I don't know what constant is. It will be just some dimensionless constant times a to the power, let's say, m, h to, no, not m, a to the power n, h to the power k, m to the power l. And a is just a dimensionless constant. I just wrote a general dependence. Well, the initial velocity is 0, so there is no v0 in our problem. Now the question is, what are the possible values of n, k, and l? There are certain exponents. What are the possible values? Now, to determine these possible values, one thing we have to make sure that the dimension of the left-hand side should be equal to the dimension of the right-hand side. Now, we know what's the dimension of the left-hand side? It's second. This should be equal to the dimension of the right-hand side. Okay, the acceleration has dimensions meters per second squared, so if you take the nth power, it will be m to the n divided by second to the 2n. H has dimensions meters. H to the k will have dimensions meters to the k. M has dimensions kilogram, so m to the l will be kilogram raised to the power l. So this is what we know. Okay, so what is the power of kilogram on the left-hand side? There is no kilogram on the left-hand side, so there shouldn't be any kilogram on the right-hand side. So L should be 0. What is the dimension of power of seconds on the left-hand side? So what is the power of the seconds on the right-hand side? Minus 2n. So this tells you that n should be equal to minus 1 over 2. What is the power of meters on the left-hand side? 0. What is the power of meters on the right-hand side? And we already know that n is minus 1/2, so k should be plus 1/2. There is only a unique solution. So this tells me that, okay, so let me just copy these. So the time is equal to this constant, whatever that constant is. Xn is minus 1/2 and k is plus 1/2. And L is 0. Or let's write it in a different form, h over a square root. Or if you solve for h, is 1 over this unknown constant, a times t squared. Now this is exactly what we had before. The height is 1 over 2a times t squared. We didn't do any integrals, we didn't do any area calculations, but nevertheless the height should be, at least if we just drop it from a height h, if it falls down to the ground in time t with constant acceleration a, this should be the relation between h and a and t squared. So it automatically already, although we didn't solve anything, just some algebraic equations, we already know that if a is constant and if you increase h by a factor of 4, for example, the time it takes to fall 4 times distance is just twice as much. We didn't solve anything, but we can still make such conclusions. And what is this A? Explicit calculation. Just tells us that A should be equal to 2. Now this is in fact always the same, in the sense that you have the parameters of your problem as A, H, and M, and you want to calculate the time. There is, most of the time, there is only one parameter, one combination of these parameters of your problem that gives you the correct dimension. And once you find that combination, all the other long calculations that you will have to do will be mainly to evaluate this dimensionless constant A, and which almost always turns out to be a number of the order of 1. It can be 10, it can be 1 over 10, but it will never turn out to be something like 1 million. It will always be a number very close to 1. All those pages and pages long calculations will be just to give you this number, which is close to 1. Now, of course, this was a simple problem which we could actually explicitly solve, but even in cases where you cannot actually solve the problem, still you can find these relationships between the parameters. So how does t changes if you increase h by 4? And this just tells you that too, without any solving any differential equation. Now, any questions on this one?
Can constant have a dimension?
No.
Like, if there was Stephen Boltzmann constant, it takes some dimensions.
Well, you see, in this problem, we don't have a Stephen Boltzmann constant. Or in that case, in fact, the reason why we have a constant called the Stephen Boltzmann constant is we want to measure the temperatures in terms of Celsius instead of the joules. If you measure the temperature in terms of the joules, we don't have such a constant. And all those constants, I mean, you see, Celsius is something we define, just like 1 meter is something that we define. Nature doesn't care about 1 meter or the Celsius. If you write your problem in terms of what we call the natural units, they just disappear. This one. Well, if you don't know the solution, you don't know whether the time depends on m or not. And in fact, here there is another proof that the time it takes for an object to fall from here to here, if it is moving with constant acceleration, if a is constant, it cannot depend on m. That is what we are proving. Of course, again, in this example at least, we could explicitly solve the problem, but such an analysis you can even do for problems in which you cannot explicitly solve the problem. And about your question is, can there be, the constants can have a dimension? Well, the relevant constant over here is a is just a constant. It's a dimension full constant. But temperature will depend on a with some dependence, I don't know what. This thing over here is something that I insert. It cannot have a dimension. Okay. A squared. No, it's just an unknown constant. Yeah, I mean, you should correct me if I do such mistakes. So if we summarize what we know about the motion in one dimension, is constant velocity. We know that v at the time t is equal to v0 plus g of t. Of course, assuming that the acceleration is downward and that is our positive direction. Okay. If we assume that the positive direction is upward, this sign over here will be minus. And z of t is equal to z0 plus v0 of t plus 1 over 2 gt squared. Now from here you can do all kinds of manipulations. Like you can solve for t and substitute it over here, you will get a relation between z and v at different points, and most of you, my impression is that the students that come to here, you already have memorized all those formulas but forget them. I mean, in the exam, you will be given these formulas, these two of them, and if you want to use any other formula, you will have to first derive them. Okay, don't forget that you cannot just memorize formulas and solve them. You will be given a list of formulas, you can use them without deriving, but if you want to use any other formula, you will be deriving them. Now, one common mistake is, what is the sign over there, v0 plus gt or v0 minus gt? That's one problem about memorizing formulas, because when you memorize formulas, you just memorize this one. You don't You cannot memorize under which assumptions you drive this thing. So that would lead you to make mistakes. So I would suggest you not to memorize formulas. In the exam you will be given the formulas. Just try to understand and learn the steps that are necessary, the assumptions under which these formulas are valid. For example, these two formulas are only valid if you have constant acceleration and the upward direction, the positive direction is downwards. If the positive direction is upward, both this and this will change sign. And you should be able to understand why it changes sign. Now, any questions on this?
In the exam, will we deal with significant figures like error?
No. I mean, you should be dealing with them in your experimental course. And if I want you to deal with significant figures and error bars, I will ask you explicitly. Any other questions about motion in one dimension? Because if not, I will be switching subjects.
How can we find the dimensionless constant?
You have to solve the problem explicitly, not by dimensional analysis. You see, for example, if you have a problem in which, not in this one, but it might turn out that you are looking for some parameter, some dimensionful parameter, and the parameters relevant for your problem, you cannot form a combination from them that will give you the parameter that you are looking for. In such a case, then A should be 0. But other than that, you cannot determine A just by looking at dimensional parameters. The only thing you can say is, it is something close to 1. Now that is even that is a big claim, because you see, what we call a back of the envelope calculation. Let's say that you are trying to study the atom. We know that typically its size is very small. So if you have a model, if you have a question, and within your model you make some calculation just by looking dimensional analysis, you obtain such a combination that will give you the size of the atom. You know that this dimensional constant can be something of the order of 1. So if this combination turns out to be 1 kilometer, then you know that what you have done is definitely wrong. Or your model is definitely wrong, it cannot be true. I mean, this constant cannot be just, it cannot be very small. It should be something around 1. By the way, this dimensional analysis is also a means of checking your answers. For example, if you are following the discussions in Octo class, there was some, I think it was the one-dimensional motion example, where you have t, somebody was saying that t was equal to some distance divided by v initial plus v final. If you check the dimension, this is definitely wrong. So you carry out your derivations, you have many steps, like let's say 10 steps, and at the end of the 10th step, if you get this expression, you say this is meters, meters divided by square root of meters per second just gives you square root of meters times second, which is not second. So this is definitely wrong. So if your dimensions are correct in the first step, but they are wrong in the 10th step, so you can figure out at which step you made the mistake, just checking the dimensions at the end of each one of the steps. And you can find where you made the mistake. Other questions? So let's start with vectors. Okay, we were up to this point, we were discussing one-dimensional motion. In the case of one-dimensional motion, it was kind of easy to specify the position of my object. Because what we had done was, okay, so this was our one-dimensional line along which my object moves. We chose some reference point, and we just measured the distance from our reference point to the position of my object. So we had also chose some positive sense, some negative sense. So it was on the positive direction, plus that distance gave me, I could just use it as the position of my object. Or if it was in the negative direction, I could say that the minus the distance was my position of the object. But when we want to describe motion in 3 dimensions, like the everyday object, if you just throw this thing like this, it makes some complicated motion. It doesn't move along the line. I have to, this one-dimensional description wouldn't be enough. So we have to first describe a means of specifying the position. So, if you just follow the trajectory, you can say that, okay, at t equal to 0, it was over here. In that direction, at that distance, at a subsequent time, it was in that direction, at this distance, and at a later time, it was at that point, in that direction, at that distance. So we have to specify these two things, in which direction and at what distance. Again, we measure the length from our reference point. We have the length, if you take this, my arm, my shoulder as the real reference point, so I can just say it's in that direction. I have to specify the direction, and I also have to specify how far away it is in that direction. So at direction, plus the magnitude. This is basically what vectors are. It's something that contains both of these information. Now in the one-dimensional example, it was the plus and the minus signs that carry this direction information, but in the more general three-dimensional motion, we cannot just use the plus and the minus because we have more than 2 dimensions. Now we can just, okay, so if you want to talk about the position, we said that you have to specify the direction relative to your reference point and also the magnitude. Okay, the magnitude changes depending on what you want to discuss. If you want to discuss the position, it will be a length. If you want to discuss for example, the velocity, we will define the velocity. In that case, the magnitude will be the speed. Or if you want to discuss the acceleration, it will be something meters per second squared. But for all of these quantities, we will be defining vectors, and they will all have one direction and one magnitude. Now, if you remember what we did in the one-dimensional case, now we talk about delta x displacement. And we define delta x as the final position minus the initial position. In the 3-dimensional case, or even 2-dimensional case, let's say, we will again talk about the displacement. Okay, we will show it in this form. This will be our displacement vector. So let's say if I'm standing here initially, if I move 2 meters in this direction, I will say that, okay, my displacement is 2 meters in that direction. That's my displacement vector. I specify the direction and also the magnitude. And we can also define it in this form as the differences of my final position and the initial position. But then the question is, how do we define the difference of 2 vectors? Or if I write it in a different form, both of them, now the question is, how do I multiply a vector with a number? And how do I add 2 vectors? Okay, before we go on, just note a few things. When you talk about vectors, you always put the vector sign to make sure that it is a vector. In your book, in most books, they use bold-faced letters. But when you're writing down with your pen or pencil, you will not be able to use bold-faced letters, so you have to put this vector sign to make sure that whoever is reading it understands that it's a vector. So just like if you forget the units, you will lose points. If you forget the vector signs, you will also lose points. So if it is a vector, make sure that you explicitly specify that it's a vector by putting this vector sign. Because without the vector sign, we will also define it in a moment, it will mean something else. Now, without the vector sign, it just means the magnitude. So I say R, this is the vector, R, this is the magnitude of the vector R. So you have to make sure that you know the distinction between these two. So let's start with the vector R and multiply it by a number A. Now, we will define, here we are defining how we want to multiply vectors by numbers. We will define this thing, assume we know this vector R. We want to define the product of the vector R with a number A. This is just a number. It can be 4, 5, minus 2 meters per second, etc. It's just a number. This will be a vector. So we define it as another vector. Now, if it is a vector, we have to be able to know its direction and the magnitude. So every vector is defined by its direction and magnitude. So if I tell you that something is a vector, I have to tell you, or I have to tell you how to calculate its magnitude and direction. So now this quantity is a vector. So now I have to tell you what is the direction of this new vector and what is the magnitude of this new vector. Now this will be, okay, the magnitude of any vector. We also denote it by the absolute value of that vector. Okay, in the case of the numbers, the absolute value is just for negative numbers, you just get rid of the minus sign, that's the absolute value. For vectors, the absolute value of a vector is its magnitude. For example, if you have the velocity, if you take its absolute value, it will be the speed. Why? Okay. Okay, so this whole thing is a whole expression. This magnitude of vector R is, we also use this symbol, this notation to denote it. Now, if A times R is a vector, first let's define its magnitude. Now, the magnitude of A times R is nothing but the absolute value of A times the magnitude of R. This is how we define it. So if R, let's say if R is a vector in that direction, 2 meters in that direction, twice that vector will be 4 meters in that direction. I just multiply the magnitudes. Now the direction is a bit more complex. Let's say the direction of A times R is equal to direction of R if A is positive, opposite direction if A is negative. This is independent of the magnitude of A, because the magnitude affects the total magnitude of A of R, but the direction depends only on whether A is positive or negative. So if I say that, okay, a given vector R is 2 meters in that direction, minus 0.1 R is just 0.2 meters in the opposite direction. So if you multiply a vector by a negative number, if A is negative, it just changes its direction. So that's one thing you have to keep in mind. Now if you go back to this displacement vector, we want to multiply this a given vector by -1 first. Now we know how to calculate that vector. It's just its absolute value of R absolute value is 1. So this vector over here has the same magnitude as this vector. Since it's a negative number, it just points in the opposite direction. Now, any questions up to here? Okay, so if you want to specify both the direction and magnitude of a quantity, you have to use vectors. That's what we call vectors. And if you want to multiply a vector by a number, what you do is the new vector, the magnitude of the new vector is the magnitude of the old vector times the absolute value of that number, and the direction of this new vector is still parallel, but it can be either in the same direction. If that number is positive, it will be in the same direction. If it is negative, it will be in just the opposite direction. Now in this case, you can just think of this as, it's just as if it's a one-dimensional thing. If you have a single vector, that will specify one direction. And if you multiply it by a number, it's just like multiplying it by a number in one dimension. So if this is your reference point, if it is 2 meters in that direction, if you multiply it by 2, it is 4 meters in that direction. If you multiply it by -2, it will just go to the negative sense. It's -4 meters in the opposite direction. Now let's discuss the addition of vectors. Now suppose you have two vectors. Okay, when you think about the addition of vectors, you can just think of vectors as, okay, we said that vectors are direction and the magnitude, but you can, at least if it is a position vector, you can think of it as a recipe. In the sense that if I tell you that that pen over there is like 2 meters in that direction, I am telling you that you should go 2 meters in this direction to find this quantity. If I tell you that, okay, your friend over here, what's your name? Denise is just like 3 meters from the pen in that direction, and I tell you that the pen is just 2 meters in that direction. If you want to find Denise, what you have to do is just move 2 meters in this direction until you reach the pen, and then 3 meters in that direction until you reach Denise. So your total displacement will be from that point to that point. So that is the position vector. That will be the position vector of Denise. So let's see, if this is the position vector of that pink pen over here, pink marker, and then Denise, the position of Denise is, this is, let's say, A, this is B. This is the position vector of Denise relative to that pink marker. What I should do is I should first bring this vector to the end of this point, because I know that this is the position of Denise relative to the pink marker, not relative to this point over here. So I should first move it over there. And then this is the position of Denise. Let's say this is the vector C. C is equal to A plus B. This is how we define the addition of two vectors. Now you can also draw this line over here. This will be parallel to the vector A. It will have the same magnitude and the same direction. So this vector is the same thing as this vector. And this vector over here is the same thing as this vector over there, because we have just moved the vector B from this point to this point. Now, so this is in a sense the proof that A plus B should be equal to B plus A. So A plus B just tells you first go over A and then over B. B plus A tells you first to go over B, then over A. So this is how we add the vectors. So let's see, what is A minus B? Let's say the vector D is equal to A minus B. How can we show this vector on this sketch?
Vector B but opposite dimension.
So it's like your friend is saying that this is nothing but A plus minus B. So first of all, what is minus B? And your friend has just said that minus B is vector B just pointing in the opposite direction. So this is minus B. It has the same length, it just points in the opposite direction. And if you just add these two vectors, first minus B, then the vector A, you start from here and at this point, so that is the new vector A minus B. Or here we define it to be the vector D. So this is our vector D. So we know how to subtract vectors, how to add vectors, how to multiply vectors by numbers, but that is basically all the things that we had done to describe the one-dimensional motion. We subtracted positions, we multiplied the positions by numbers, which are just the inverse time, those are just numbers. So we can just repeat everything in 3 dimensions using vectors already. But before going, we need to, any questions on this one? Up to this point about vectors. Now at this point, if you see something that has both a direction and a magnitude, you can always think of them in terms of as if they are vectors.
What about time?
Does it have a direction?
You always take it going forward.
What is the forward direction? Can you show it to me?
Not in 3D maybe, not in 3D-dimensional,
Mm-hmm.
but it does mean time has no dimension.
Well, I mean, it has a dimension, but I mean, at least in 3-dimensional space, it doesn't correspond to a direction. So that's, in 3-dimensional space, it's not a vector. Of course, with Einstein theory, he kind of unified space and time. Then in that case, time is just like x, y, and z directions. It will be part of a vector, but even in space-time, the time is not really a vector by itself. Other questions? Is there anybody who didn't do their add drops yet? You see, there are these, the ends of the lectures, the last 5 minutes. It just doesn't worth starting a new subject, but I also don't want to let you go. These are what I usually use for quizzes. No, not today. After the add drops, we will start. If no questions, see you on Thursday.